Hello, everyone. Welcome to Ask Seminar Series. This is the first one in the spring, and now we have over 60 attendees. So I'm John, the seminar coordinator, and I'm with Ms. Kathy Medany. And so Kathy is our communication specialist, and Kathy and I will be today's moderator. Today, we are excited to have our distinguished speaker, Dr. Collins, joining us from Berkeley. Just a few things before we get started. So the seminar is being recorded and it will be later published on our YouTube channel. Please feel free to ask questions. You can do so by raise up your virtual hand. We will unmute you, or you can send us a message. Let me give a brief introduction about our speaker. Dr. William Collins is an internationally recognized expert in climate modeling and climate change science. His personal research concerns the interactions among greenhouse gases and aerosols, the coupled climate system, and global environmental change. Dr. Collins is a fellow of American Association for the Advancement of Science, the American Physical Society, and the American Geophysical Union. He was awarded the AGU's Tyndall History of Global Environmental Change lectureship in 2019. He was a lead author on the fourth assessment of the Intergovernmental Panel on Climate Change, IPCC, for which the IPCC was awarded the 2007 Nobel Peace Prize. And he has and will serve as lead author and coordinating lead author on the fifth and upcoming sixth assessments. His role as chief scientist in launching the Department of Energy's Accelerated Climate Model for Energy program was awarded the U.S. Department of Energy Secretary's Achievement Award in 2015. Before joining Berkeley and Berkeley Lab, Dr. Collins was a senior scientist at UNCA and served as chair of the scientific steering committee for the DOE NSF Community Climate System Model Project. Dr. Collins received his undergraduate degree in physics from Princeton University and earned an MS and PhD in astronomy and astrophysics from the University of Chicago. So let's welcome the speaker, and Dr. Collins, please proceed.
Much, John and Cassie, for arranging the seminar today. It's really an honor to be able to present to you. Let me see if I can share my screen with you. Excellent. So I thought I would devote this lecture to work that we've been doing as part of a project that I lead called Cascade, which is devoted to looking at climate extremes. And this work is joint with a pretty large team of collaborators, primarily at Berkeley Laboratory, but also with a scientist named Travis O'Brien, who was a colleague at Berkeley Lab and has recently joined the faculty at Indiana University. And much of the work on the Bayesian detectors, I'll be speaking about a little bit later, is really Travis's primary research. So what we have been trying to do is understand how to detect climate extremes in the torrents of climate model data being generated for the sixth IPCC assessment and also in satellite data. And that has led us to really focusing on issues around uncertainty quantification. And I think the reasons for that focus will become evident a little bit later in this lecture. I should point out that this research is sponsored by the Department of Energy through their Office of Biological and Environmental Research. We've also benefited tremendously from the NERSC Supercomputer Center that's located at Berkeley Laboratory. So as sort of an emblematic type of extreme that's very important to the state of California, I'm going to focus this lecture on atmospheric rivers. And it's timely that I'm talking to you about that now because California, as you probably know, has a Mediterranean climate. And our rainy season actually runs from roughly November through the end of February, March, and we're in the middle of the rainy season now. This entire week, with the exception of today, is slated for rain. And much of that rain during December, January, and February is brought to the state in the form of relatively severe storms known as atmospheric rivers. And the parochial term for these is the Pineapple Express. These storms can take, or are highly beneficial. They provide the state with the roughly a third of its total water supply. The state relies on 80 million acre feet of water, and about a third of that is trapped in the form of snow in the Sierras, deposited this time of year thanks to atmospheric rivers, so they're extremely important. But they also can take a slightly more damaging turn, as shown in the two pictures or graphs on this slide. The most recent incident that nearly became life-threatening was the failure of the Lake Oroville Dam, a spillway that occurred 4 years ago, in which the dam began to suffer some fairly major failures in its infrastructure, and fortunately did not utterly collapse, but came relatively close. And the graph on the right shows you the how higher percentile of this particular year was relative to background, and it's in the upper, close to the 95th percentile of rainfall that the state has experienced in recent recorded history. And this is thanks to data from the Department of Water Resources from the state of California. So we do monitor these both as both a boon and perhaps a bust for the state. And when we began looking at these phenomena as part of Cascade, this project that we were running for the Department of Energy, I'm a big believer as a physicist in defining my terms before I start to work on problems. And the definition of atmospheric rivers, and this is taken literally word for word from the American Meteorological Society glossary, are long, narrow, and transient corridors of strong horizontal water vapor transport. So that is a relatively qualitative description of these phenomena. And as I'm going to show you in a moment, the lack of a precise definition has led to numerous sort of ad hoc methods for detecting these, both in satellite observations as shown in this picture, and also in model data. So there's essentially no theoretical or community accepted definition or standard for what these rivers are. And that has led to a fairly large ambiguity in the literature. To begin to address that ambiguity, roughly 2 years ago, the Department of Energy launched a project called ARTMIP. And for those of you who are part of the modeling community, these MIPs, the acronym MIP is a very familiar acronym. It stands for a Model Intercomparison Project. The 6th IPCC assessment is relying on something called the Coupled Model Intercomparison Project version 6, or CMIP6. And what ARTMIP is it's actually a method intercomparison project. And the ART part of that is the Atmospheric River Tracking Method Intercomparison Project. And the goal of ARTMIP is to take different methods for tracking atmospheric rivers and understand what's common between them, what differs between them. And this is work that's been led largely by a former colleague of mine from NCART, Christine Shields. And you're welcome. I invite you to go look at this paper that appeared in the Bulletin of the American Meteorological Society. It's no longer in press, it's been published, where they describe the goals and objectives of ARTMIP. And I'm going to show you several results from ARTMIP just to sort of tee up our focus on uncertainty quantification around atmospheric rivers going forward. One of the early results out of ARTMIP is this graph. And what it's showing you is for the December, January, February season as a function of detector along the horizontal axis. So the horizontal axis is literally numbered by different algorithms that have participated in ARTMIP. And the vertical axis is the area of atmospheric rivers detected by these various algorithms. You'll notice it's a logarithmic axis. And we've put on there, just to be somewhat tangentious, a horizontal gray dashed line, which is the area of California in these units. And what this graph makes fairly clear is that the range of areas detected by the algorithms participating in ARTMIP varies by approximately 3 orders of magnitude, from 1/100th of the area of California to close to 10 times the surface area of California during any given season, with the bulk of the algorithms being slightly above the mean area of California, but a few of them being dramatically below. And one might ask, well, this also has very practical implications in terms of the amount of rainfall being deposited in the state as projected by these algorithms, the amount of vapor being transported by them. This uncertainty in their surface area translates into other properties that are quite important for understanding their impact on the hydrological cycle. So another way of characterizing this and bringing this back into the language of the coupled modeling and comparison project that I described earlier is to ask the following question. If I look at sort of now an uncertainty space that's spanned by detectors along one axis and climate models along the other axis, which source of uncertainty dominates? And so what I'm showing you here is on the lower right-hand part of this slide is that two-dimensional phase space. On the vertical axis are different models from the coupled modeling and comparison project. And I believe these are CMIP5 models in this case, and CMIP6. And along the horizontal axis are different algorithms. And the one of the rows in this diagram is blown up for reference in the upper part of the slide. And the titles on each of the frames, like AR Connect, IDL Relative Future, LoRa V2, ModHank, and so forth, Tempest, those are all names for different AR detectors. Notice if we go back to the diagram on the lower right-hand part of this slide, is that in the vertical, and these are depicting now changes over the 21st century relative to the historical record, that the models agree with each other much more than the algorithms do. So in other words, along the vertical axis, the change that you see, say from the signal predicted from AR Connect, which is predicted that there'll be more atmospheric rivers in the 21st century than in the 20th, that's a common signal across the climate models. But the algorithms disagree pretty significantly. So, for example, the Tempest algorithm indicates that there will be dramatic drops in the number of atmospheric rivers in the Northern Hemisphere storm tracks in the 21st century relative to the 20th century. So that is a sort of what I regard as a fairly substantial outcome of the ARTMIP project, that we can't agree on how atmospheric rivers are going to change over the 21st century, which has major implications for the water supply in the American West and in Europe and in South America. And this is another way of plotting the same data. So if you focus on the right-hand graph, which is the change in the number of atmospheric river days and just counting them as a function of longitude, what this graph makes evident is that the uncertainty from models is a relatively insubstantial fraction of the total, and the algorithms dominate the total uncertainty in the number of days where you would count an atmospheric river incident on the coastlines of, or count them in various ocean basins. So again, this is just the same way of saying that algorithm uncertainty dominates. Now this has implications, and this is the last thing I'll say before diving into the subject around Bayesian detectors, where I'll spend the bulk of this lecture. This has implications for machine learning. in the following sense that for machine learning algorithms that are supervised, where we're providing them with a training data set, we have to train them on a data set where the rivers have been labeled. And what I've been indicating to you now that those labels from one algorithm to the next have a very high uncertainty. Now, one way of embracing that uncertainty is then to say, fine, we're going to be totally agnostic as to the relative value of any one of these algorithms. And what we're going to do is train a machine learning algorithm on the locations on the planet where as many as the algorithms agree as possible that there's an atmospheric river present. And we actually ran that exercise as part of the research that we were doing under Cascade. This is work that was done by an undergraduate named Ankur Mahesh, who's now a graduate student of mine. And what's shown in this figure is our so-called AR confidence index, which is simply the it's 0 if all the algorithms agree that there's no river present, and it's 1 if all the ARTMIP algorithms agree that a river is present. And so you can see that when the algorithms all agree, you get these plausible looking, sort of long, linear looking structures. And you can see in this figure, for example, there's an Atmospheric River incident on the west coast of the United States. And there's another Atmospheric River that's forming over the western part of the North Pacific Basin. So you can train an algorithm to do this for what it's worth. And for this, we use convolutional neural networks that are in the same kind of convolutional neural networks that are used for pattern recognition in smart cars and so forth. And my now graduate student, Ankur Mahesh, took the ground truth, which is shown in this upper right-hand panel, which is the something known as the integrated vapor transport, ran it through a convolutional neural network, and got a machine learning algorithm to agree almost perfectly on where the combination of these ARTMIP algorithms said one should find a river. And this movie now illustrates beautifully what that looks like, and it's a very plausible rendering of where the ARTMIP algorithms all agree that one should find rivers. However, this is not actually it's effectively the ARTMIP form of an uncertainty analysis that we've been doing in the Temple Modeling Comparison Project, where I just ask where do models agree. Here we're asking where do methods all agree. It says nothing about whether or not the methods actually stand truth. And it says nothing about whether or not any one of the model or the methods, detection methods, is more accurate than any other method. And it says nothing about whether or not any of the methods are actually more grounded in the underlying fluid mechanics of the atmosphere than any other method. So we have concluded within Cascade that this is an inherently unsatisfactory usage. And for that reason, we've gone back to what I regard as basics and asked, can we build a detector that's as simple as possible to do a very simple thing, which is to count the number of atmospheric rivers in the atmosphere at any given time and ask how uncertain is that answer? And let me just note at this point, someone on the on this lecture has their microphone unmuted. So if all of you could check to make sure that your microphones are muted, that would be most helpful. So what we're going to do now is take reanalysis. In this case, I'm showing a result from Arrow 5 reanalysis, but we're going to focus most of the bulk of this work on mirror reanalysis from the Japanese mirror product. What we're going to do is take integrated vapor transport, which tells us how vigorously there are rivers, and then train a Bayesian algorithm to reproduce the expert. to embrace that these are uncertain. And these uncertainties will cause actually differences in sign. I'm going to show you next. So we're going to have an algorithm that looks for places where there's a high amount of vapor transport. The basic
Dr. Collins, can you hear me? I think there's something wrong with your audio. It keeps coming back in and out.
The reason is that someone is in a someone on the call has their microphone unmuted. Cassie, does it look like it's okay now for me to proceed?
Yeah, I think so. Everyone should be unmuted, but I did expel someone that's name was popping up. But yeah, no one should be unmuted now.
Let me try moving forward. I'll restart the point I was making about this slide. So what we're going to do is build a method for counting rivers that's based on counting places where there's a large amount of transport. We're going to exclude the ITZZ because that tends to be a very confusing place to try to look for these weather phenomena. And we're going to eliminate small patchy regions of transport that are too small to fit the AMS definition of what a river is. Okay. So the goal here is to set sort of three different criteria: a threshold for vapor transport, a minimum area for these transport, and a minimal and a sort of a width of these, a width or size of these candidate rivers. We're going to be very agnostic about what these criteria are and then constrain them using expert knowledge about what rivers look like. So imagine that I come to you and say, we're going to set three parameters, very agnostic about what they are at the beginning, and we're going to constrain them using expert counts of rivers in actual data. So what Travis and others did was run workshops where we showed participants at those workshops, and as it turns out, roughly 9 participants, maps of integrated vapor transport, and asked them to hand label where the rivers were in images of integrated vapor transport. And this is an instantaneous snapshot of what that looks like. So the yellow circles indicate places where this particular expert said, yes, there's a river present. And this particular expert counted 1, 2, 3 rivers in the Northern Hemisphere and 1, 2, 3, 4, 5, 6 rivers in the Southern Hemisphere. And we use these counts to then constrain the parameters in a Bayesian optimization algorithm. And I'm going to show you one slide that has some math on it. But that, fortunately, that will be one of the very few slides that has math on it. So on this slide, I'll just walk you through it briefly. N, capital N, is the number of counts that came from these experts. Q, in this case, is integrated vapor transport. And theta are those 3 disposable parameters I described to you earlier. And our goal is to optimize theta such that we reproduce these counts as accurately as possible. Travis built a Monte Carlo, a Markov chain Monte Carlo algorithm that will perform this optimization, and was very successful in managing to reproduce these expert counts of atmospheric rivers, as I'm going to show you in just a moment. But this is the underlying mathematics that went into this scheme, and the beauty and the important feature of this algorithm is that it's coming back and saying, not giving us one specific setting on these 3 detection parameters, because that's that characterizes all the algorithms in ARTMIP. They all have one set of parameters. In this case, it's coming back with a probability distribution for those parameters and saying, here's the likelihood that this particular parameter setting reproduces what the experts told me. And it turns out that that's really key for what we're going to be doing with this algorithm going forward. Okay, great. So now what we can do is, this goes back to the diagram I showed you earlier. And remember, I showed you that there were these various X's where the experts claimed that there was a river. So here's an X, here's an X, here's an X. There are 4 X's in the Northern Hemisphere. And the green contours on this diagram, so the bold green contours, are where this probabilistic algorithm says, I detect a river at a pretty high level of confidence. And sure enough, the algorithm is encircling each of these X's with a high degree of confidence. And we can summarize this information like so. So on the horizontal axis are the, in any given sort of season, are the counts from these various rivers, atmospheric river experts. There were roughly 9 of them all told. And these experts said there are as many as 12 atmospheric rivers at any given time. So when we showed them an image, they said, yeah, I count anywhere from roughly 3 up to as many as 12 atmospheric rivers at a given time. And you can characterize that information by season. So it's December, January, February, March, April, May, June, July, August, and instead of October, November. On the vertical axis are the atmospheric river counts coming from the algorithm. And the point of this figure is to show you that the algorithm does a really nice job of reproducing what the experts told us. So that's reassuring. So there's one final thing to leave you with before I dive into kind of the so what message from now having a probabilistic detector. And that is to indicate that these experts disagree in some pretty fundamental ways. And one of the ways they disagree is about the relationship between atmospheric rivers and the presence of El Niños. There's a whole cottage industry in the literature, pardon me, devoted to correlating ENSO activity with the amount of atmospheric river landfall on the coast of California. Members of my Cascade team have looked at this and claimed that it's primarily a dynamical phenomenon, that there are favorable conditions that arise during different phases of ENSO that lead to more favorable landfall conditions for atmospheric rivers on the coast of California. So there's a very large body of literature that has looked at this. So if we now, if we now ask for what's the relationship between an index of El Nino activity and positive on this index, on the positive values in this vertical index indicate greater El Nino activity in the central to the eastern part of the Pacific Ocean, in other words, in the positive phase of ENSO, and negative indicate more activity during La Nina. What you find is that by the different experts that we asked, in this case there were 8 of them, the correlation between the atmospheric river activity and this index goes positive or negative. In other words, the experts literally disagree. When you have favorable El Nino conditions, you get more or less atmospheric river landfall on the coast of California. So rho here is the correlation between count and a particular measure of ENSO activity. Some of the experts said it's neutral. So expert 0 said there's no correlation between the number of rivers making landfall on the coast of California and El Nino activity. 4 of them said it's weakly negative, and 3 of them said it's weakly positive or positive to weakly positive. Now, the reason I'm mentioning this is not to call out these 8 particular experts, but to point out that these 8 experts are characteristic of the community that designed the ARTMIP algorithms that we started this lecture with in the beginning. So these 25 algorithms we've been discussing as part of ARTMIP were each designed by Amherst River experts who are, from which these 8 experts are effectively drawn. And now you can begin to understand why there's such a disparity among the ARTMIP algorithms. It's because these experts can't even agree on whether or not El Nino causes more or fewer rivers to make landfall in the coast of California, which is the subject of most of the literature around Amherst rivers, at least developed by experts here on the West Coast. And this is another way of illustrating that uncertainty just in terms of the range of counts produced by the these various experts. And I won't take you through this particular histogram, but it's making the same point. All right, so now let me come to a critical question, which is how do we use Bayesian detectors to unravel questions that are of interest to us about climate change? And in particular, can we ask the question, given that we now have a detector that comes sort of accompanied with a natural statement and mathematical statement around uncertainty, what does it allow us to do? And what I'm going to ask is, what does it tell us about the trends in atmospheric rivers over the historical record? And remember, these Bayesian detectors come not with a single set of magic numbers underlying them that allow you to detect atmospheric rivers, but with a probability distribution around those parameters. And those 3 parameters are the intensity of the vapor transport, the range of latitudes that we exclude from being detected, and how big the rivers have to be. So what we're going to do now is ask for a period of time where we sort of know what happened. So we're going to look at the historical record roughly a century. We're going to ask what are the trends in atmospheric river counts using different parameter combinations for the historical record. And this is the posterior probability distribution for atmospheric rivers during December, January, and February, which is the period of the most, which is our rainy season, the period of most intense transient activity in the northern Pacific Ocean. And this time series is starting from the year 1900 up to the year, up to present day, basically. The black solid line provides the mode of the distribution, and the gray region about that is the 5th to 95th confidence interval. And it shows you that, well, first off, it's fairly hard to see any obvious trend by eye in this time series. The counts have remained to within 20% at least, roughly constant over the historical record. But if you dig into this time series and ask for any one particular parameter setting, and again, you should regard this as being characteristic of any one of the algorithms that have participated in ARTMIP, what do you find? And when you interrogate the data set that way, so don't interrogate it from a probabilistic perspective, but ask, if I pick it, any one of these sets of magic numbers, what do I get? Well, you can actually reproduce or find fairly substantial, moderately substantial trends in the number of atmospheric rivers over the 20th century. This is in units of count over 100 years. And those trends actually span 0. So they range all the way from saying that the number of atmospheric rivers has declined slightly over the 20th century, all the way up to there's a reasonably significant trend in the number of atmospheric rivers over the 20th century. And this starts to help us make sense of the diversity of literature that I'll come back to a little bit in a moment. And this is not by means of sort of singling out any of the people who have developed these algorithms, but simply to make the point that it behooves us to begin constructing algorithms that come dressed with an uncertainty estimate. And I've now shown you two, one, the machine learning algorithm that I showed you a little bit earlier in this lecture, and now this one. And if you take these various trends, so one that's negative and the ones that are positive, and color code the data that I showed you a moment ago. So the blue line on this graph is indicating for you one of the particular instantiations of a detector that starts at a high count and declines over the 20th century. And the thick red line, the thickest of the red lines in this graph indicates a particular detector that starts low and then trends upward during the 20th century. So one of the other unique aspects of having this particular means of constructing these detectors is that we can now begin, and I won't dwell on this, but if you wanted to go in and understand, to really tear apart, so we have a three-dimensional phase space. It's in terms of the amount of vapor being transported, the range of the essentially the ITCZ and the immediate subtropical region around it that you exclude for the detection, and the area of the rivers. You can begin to interrogate that phase space as to which combination of those parameters yields positive and negative trends. And what one finds from doing this particular analysis is that there's a strong correlation between these parameters. So, for example, emitting large numbers of small rivers tends to drive you to requiring extremely high vapor transport in those rivers. So if you're going to emit lots of small rivers, they have to be particularly intense and vice versa. And so you can begin to use this framework to understand and perhaps go back and interrogate the algorithms that are already published to understand why they're yielding such a diverse range of answers. And in fact, begin to understand why they are yielding disagreements in sign as illustrated by these three different papers. And the reason why I bring up these papers again is not to single out these particular authors, because these are all very worthwhile contributions to literature. And a number of these authors contributed algorithms to ARTMIP. But essentially to say that on the basis of a single algorithm, one might reach different conclusions about what climate change has done over the historical record and what it implies for the 21st century. So these three different papers, which are representative of the literature, in fact, reach, I'd say, mixed if not moderately opposing conclusions about the sign of the trends in atmospheric rivers based on the historical and recent model record that they evaluated. And it's for this reason that I think we need to begin thinking about this uncertainty quantification, not only for atmospheric rivers, where we have highly subjective definitions, but also for other phenomena like frontal systems, blocking events, phenomena where there's not a first principles definition that's grounded in computation in geophysical fluid dynamics, upon which the community can write down a single unique definition and around which we can all agree how to detect them. So with that, I think ARTMIP has illuminated a very important source of uncertainty for us. And I think what might behoove us going forward is to think about launching parallel method intercomparisons focused on, as I just mentioned, blocking torrential systems, especially extratropical cyclones, where again there's a tremendous diversity in literature about what they are, how to detect them. Our own work has indicated gigantic diversity in counting them. So the counts there in extratropical cyclones, again, is an area where the community has reached, I would say, a highly diverse characterization of the historical record. So this is, I think, the first of what I hope will be a number of different method comparisons. First, to characterize what's out there in terms of how we are understanding, how to detect these systems, and then moving forward, how to address our characterization of what's out there with some sensible statement about the uncertainty in it. So let me summarize what I've shown you. Detector uncertainty really matters for our qualitative understanding of climate change. By qualitative, I'm indicating not just the magnitude, but also the sign. This is an open open question for a number of important weather phenomena. As I've illustrated for you, Bayesian methods, which really sort of embrace characterizing the uncertainty and the magic numbers that underlie many of our threshold-based, both absolute and relative detectors for phenomena, is a very logical way to go. The algorithm that I showed you is now published. It's called TCAPARD. We're in the process of making this available through my Cascade project. I'd be happy if you'd like to contact me or contact Travis O'Brien to provide you with a detector. We are going to make it, and are in the process of making it a public domain detector. And we welcome your input on it and utilization of it. And last but not least, let me thank our sponsors for this. So this work is primarily sponsored by the Department of Energy through the Office of Biological Research, through a pair of contracts, both to my division at Berkeley Laboratory, but also to the National Energy Research and Scientific Computing Center of NERSC, which also happens to be headquartered at Berkeley, where we did a lot of our computing. With that, thanks, John, thanks, Cassie, for getting this seminar set up, and I welcome the questions that you might have for me. And I'm going to leave my slide. Well, let's see, what should I do here? I will be happy to come back to any slides anyone. I'm still sharing my screen, but I'm happy to flip back to any slides you might want to address in questions. So questions for me?
Thanks, Dr. Collins. I just got a question sent to me from Michelle Leheroux. But just as a reminder to everybody, if you have any vocal questions, you can raise your hand or you can send the chat message to me and I will read the question out loud. So the question from Michelle, is it possible that the reason there is a strong variability among experts about ENSO-AR links is because the relationship between ENSO and AR is just not that strong?
Well, that's an excellent question, and that is that's certainly possible. That may be part of the explanation. The other, and I think that may be a perfectly reasonable explanation for what we're seeing. I would say that the thing that has given me pause, and I'm should be still sharing my screen. So, can everyone see Can you see a histogram here?
Yep, we can.
Good. So the reason for showing you this particular histogram is to point out that when given the same data set, experts, and given the same time slice from the same set of data sets, experts had nearly an order of magnitude disagreement in the number of rivers they were seeing at any given time. So there's, I would agree that there may be weak linkages, but I think the other disagreement that we need to fully embrace is that the people designing these detectors don't agree to nearly roughly an order of magnitude about how many of the phenomena that they're seeing at any given time. And that's a problem. And that's a great question. And the reason I was stalling there for time was I was thinking back to work that we've been doing, looking at the linkage between MGOs and atmospheric rivers. And I will I will see if I can remember to get back to you to the question after this lecture with some follow up on the linkage to MGOs and see if this uncertainty question also plays out in that context as well. That's a place where we're seeing stronger linkage, but I think it's also equally uncertain if you look across experts. But I'll have to get back to you on that question. That's a great question. Thank you.
Thank you. We have a vocal question from Claudia Tabaldi. Claudia, you are unmuted.
Hi there. Nice talk. I'm curious to try and understand about this uncertainty in calling something an atmospheric river. If it has to do with real ontological problems in defining what an atmospheric river is, or if it is a problem in recognizing it either from observations or model because we don't have enough resolution, for example. And this question was triggered by you using other phenomena in the same list, like tropical cyclones, because maybe it's just me being ignorant, but I don't think people have issues calling something a tropical cyclone or not. There are measures that are pretty objective. So anyway, the question is, do you think maybe better modeling and better resolution, better observations would help nailing what an atmospheric river is, or do you think it's going to be always a problem?
Question. So let me start with going back to this figure just to illustrate that these rivers are not they're not sub-resolution phenomena, right? So they're big. They typically have lateral lengths along their long axis of a couple of thousand kilometers. So they're definitely resolved both by modern climate models, which some of the models we're looking at now have 25 kilometer resolution. So there are 80 grid cells along the long axis that resolve these things. What I think the issue for me, Claudia, is that we have not thought about these in terms of the underlying fluid mechanics. So these systems are advecting water vapor for a reason, which is part of the reason is that they're accompanied, they're usually associated with a low-level jet, and it takes work to mix the fluid from that jet back into its ambient environment. And what we are not doing adequately in defining what these phenomena are is accounting for the fact that it takes work to mix two fluids that into each other, or it can take work. And we're not accounting for that work in a geophysical fluid mechanical sense. So I've been advocating for thinking about using, for example, finite time Lyapunov exponents, which are a measure of mixing, as a means of defining rivers, and we're looking into that as one way of putting detection of these rivers onto a much more solid footing, because then it's really a measure of the Lyapunov exponents become a measure of whether or not two fluids can mix. And it's that sort of definition that I think we need to embrace, because the Lyapunov exponents can be tied back to the fluid mechanics in a fairly rigorous way. But at the moment, it's at least my personal opinion that we're having trouble because we have a definition that is highly subjective.
Yeah, it's just looking at it. Yeah. Thank you very much.
Other questions?
So we received one text question while Claudia's question was being asked. So is there any difference between microwave and IR for the detection of atmospheric river?
Any difference? Both are so both are used. You can very easily see atmospheric rivers in what's known as the water vapor band, which extends from 5 to 7 micrometers at the sort of the high wave number end of the infrared. And the reason is that part of that water vapor band can be used to distinguish water vapor low and high in the troposphere. And so the atmospheric rivers show up as very coherent linear structures. Depending on where you're looking in the vertical and the troposphere, you can sort of dial that in by wave number in that part of the band. Because water vapor also, as you know from using a microwave, strongly absorbs microwave radiation. They're highly visible depending on which band in the which window band you use in the microwave. So both detectors are suitable. And I think your question was getting at which is better. To be honest with you, I don't know. I should know the answer to that, but I don't. One can definitely use both because water absorbs strongly in both. Once you get into beyond the CO2 band, water vapor has an exceptionally broadband absorption structure, and it is that forms the basis for a lot of microwave remote sensing. Other questions for me, Cassie?
That is my list. If anyone has any questions, you can raise your hand and I will unmute you now, or you can send them to me in the chat. Okay, unless I get a raised hand while I'm talking, I think that is probably it for us. Thank you, Dr. Collins, for this great talk. Thank you, everybody, for coming. We will continue next week with our seminar series. Thanks again.
Thanks so much. Bye-bye.
Thanks, Dr. Collins. Thank you. Bye.